So we're now going to take a look at the divergence test for infinite series. It looks as follows. It's actually the simplest and most basic test for the convergence or divergence of an infinite series, and it's well worth learning. So let's take a look at it. You can formulate it in several ways, but I kind of like the one where we say that if these AKs do not tend to zero, so by this I mean not this, meaning that this limit may exist and be equal to something else than zero, or that this limit doesn't exist at all. Those are the two options. Anyway, if you have this, then this implies that your infinite series with terms AK diverges. So if the terms don't go to zero, your series cannot converge. Let's now go to the proof. This is one of the few statements or proofs in this course that we do by the contrapositive. Okay, so let's formulate the contrapositive. So the contrapositive statement would be that not this implies not this. Okay, and not this is not what's inside of here. So what we get is, well, the opposite of or the negation of this guy being divergent, that's him being convergent, implies this limit going to zero. So this is the contrapositive of this. So contrapositive. So the question if this is true is the same as the question, is this true? So now we're trying to prove this. So to prove this, what do we do? Well, notice the following. So if this guy converges, so by hypothesis, there exists a number L such that if we call the partial sums of this guy Sk, then it's such that the partial sums here, or Sn, maybe we should call them, tends to L. So I know this converges, and I want to prove that this implies that these guys tend to zero. So we note this, the following connection. If I now take Sn and I subtract Sn minus 1, so the index here is minus 1, then I have my A0 plus A1 up to An, and I'm subtracting my A0 plus A1 but not up to An here, but to An minus 1. So here I have all the numbers up to n, or An, and here I have all the numbers up to An minus 1. So the only difference between these two parentheses is this guy. So he's the guy surviving, okay? What does this mean? Well, this means that if I now take the limit on both sides, what do I get? Well, I get that the limit of Sn minus 1 is equal to the limit of the Ans as An, or as n goes to infinity. But what does this mean? So here, I know that these Sns tend to L, but what do I know about the Sn minus 1s? Well, if Sn tends to L, that means exactly that S0, S1, S2, S3, S4, S5, this sequence here gets closer and closer to L. What is Sn minus 1? This means that I'm starting out here. So when n is 0, I get s minus 1. He doesn't exist. I can put him to be 0, okay? So let's put s minus 1 to be 0. Then I have s0, s1, s2, s3, s4, and so forth. This sequence of numbers here, well, they will tend to whatever this sequence of numbers tends to. So these guys will also tend to L. So the limit of both of these guys is equal to L. So the limit of this difference ought to be L minus L, which is 0. So if Sn converges to L, this guy converges to L, the difference converges to 0, but the limit of their difference is equal to the limit of the Ans, hence this limit is 0. And we are exactly getting the desired conclusion. You may object here to the fact that here I have An and here I have AK, but I could call this Am or A flower or whatever. It really doesn't matter. Also, one can notice that here, I mean, I'm using an intuitive argument. This can be a nice little exercise when we're looking at the definition of the limit.